The goal of the project was to analyze the effective change in free stream velocity and surface roughness on the boundary layer of an airfoil. There are many reasons for the need to study the boundary layer in general. It has a wide variety of applications. Most commonly, we seek to reduce drag and increase lift in aircraft, which helps reduce fuel costs. The boundary layer also plays a role in the path of a projectile, say a golf ball. Most realistic fluid flow analysis also needs to account for the boundary layer growth at the interface of the fluid and the wall to determine, for the instance, the pumping power needed to transport fluid across a pipeline. Finally, heat transfer in devices such as heat exchangers can be controlled by modifying the boundary layer growth. The boundary layer is essentially a thin region in the flow over a body that is dominated by viscous effects. These viscous forces lead to lower fluid velocities near the surface in order to satisfy the no-slip condition at the interface. As we go far beyond the boundary layer, the fluid velocity is unaffected, and this gives rise to one of the simplest mathematical expressions for the boundary layer, where we define it to exist till the point the fluid velocity is 99% of the free stream velocity. The boundary layer may be laminar or turbulent, or transitional, which occurs between the two. This is determined by the Reynolds number, which depends on the fluid viscosity, density, free stream velocity, and the characteristic length, which depends on the geometry one is dealing with. Our airfoil design was based on the NACA 63212. As we wanted to evaluate the effect of the surface roughness on the boundary layer, we created a simple smooth surface and a rough surface. The parts were 3D printed using PLA, polylactic acid, as shown. This airfoil has been used in a large number of aircraft, some of which are shown here. The solution to the boundary layer over a flat plate is the simplest case possible. Analytical solutions such as the Blasius solution are possible by solving the Navier-Stokes equation, due to the fact that there is no pressure gradient in the x direction. On the other hand, the flow over an airfoil is highly complex, due to which no analytical solutions are possible. The complexity arises due to the need to account for a pressure gradient that is present here, which is influenced by the airfoil profile and the angle of attack, which makes a theoretical solution difficult. Here we can see our experimental setup with the water channel being on the top and our pump being on the bottom. Here we can see the reservoir tank with the dye reservoirs and dye injectors on the side of the channel. Behind, here's the studio lights to illuminate the part with a blank background. Here inside the channel, we have flow from the left to the right with the dye injection needle to show us that. Here we see our smooth airfoil at our lowest pump speed. This flow is considered very laminar, as we can see with the boundary layer being very well defined and very clear. Here we can see at the same pump speed, our rough airfoil demonstrates the same kind of laminar boundary layer flow, but we see it sticking closer to the interface rather than smooth due to its surface roughness. At this flow, at a faster pump speed, we see that the boundary layer displays more of a turbulent type of quality, as we can see with the dispersion of the dye in the wake zone behind the airfoil. This type of flow is shown in both the smooth and rough airfoil flows. Here at our fastest pump speed, we see the boundary layer display its most turbulent type of flow and turbulent type qualities, as we can see with the dispersion of the dye with the very fast flow going past our airfoil. Here with our rough airfoil at our fastest pump speed, we can also see its most turbulent flow. As with some of the other videos we see that the boundary layer tends to stick to the rough surface a little bit more than the smooth surface due to its surface roughness. Here we have our pump curve with corresponding flow speeds corresponding with the hertz of the pump.
Here is the summary for the airfoil with the rough profile. We can clearly see that the boundary layer thickness is decreasing with increase in flow rate. We have added a red line that traces the boundary layer in order to help with the visualization. And this summarizes the airfoil with the smooth profile. We see a repeat of the trend here, that is, the boundary layer is decreasing with increase in flow rate. Here is a graph that summarizes our data. We have the boundary layer thickness plotted on the y-axis versus the flow speed plotted on the x-axis. The orange and blue lines represent the smooth and rough airfoils respectively. We can see that not only is there an inverse relationship between the two, but also that the lines are nearly linear. There is a difference between the slope of the two lines, but that also has to do with the difference in angle of attack. And with that, we conclude our presentation. We have shown that the boundary layer thickness decreases with increase in flow speed, and the relationship is nearly linear. However, we noticed a difference in the angle of attack between the two sets of experiments, which is why we weren't able to compare the effect of surface roughness. While we have focused on the change in boundary layer thickness, we have found research articles that have focused on the change in lift and drag forces with change in Reynolds number, achieved by changing the flow velocity. Experiments from a NACA article focused on this aspect. They have shown that the decrease in Reynolds number has corresponded with a decrease in maximum lift while at the same time increasing the drag forces.